Welcome back class to our course on mechanical behavior of materials part 2. So in the last lecture we discussed about ductile fracture mechanisms. Okay, and today we are going to talk about brittle fracture mechanisms. Okay. Okay, so here we are going to talk about nucleation and growth of cleavage fracture. Okay. Cleavage, I have already discussed that the fracture is occurring along a particular plane. So it's like cleaving, right? So this is called cleavage fracture. So we will first talk about the nucleation part, and then we will talk about the growth, where I am going to introduce you to different kinds of patterns which can be formed during cleavage fracture. Okay. So nucleation. So two things can happen. You can have a crack, pre-existing crack, and then from there you are going to have a growth of cleavage crack. Okay. Or second, you have to nucleate the crack. Okay. So the first is, if a material contains sharp pre-existing flaws or crack, okay, then two things can happen, right? The first is that this crack will grow. And remember, these are in mode 1. Okay. So mode 1 becomes very important here. So you already have a crack. Now this crack itself is growing and it is leading to the cleavage fracture. Second can happen that the pre-existing crack, right, that can create another crack in front of it, and then it will combine and then it will lead to the cleavage fracture. So it might nucleate crack ahead of the main crack. So in this case, main crack is your pre-existing crack. Okay. And then it will lead to the growth of the cleavage crack, and then there will be fracture. Okay. So first one, this point number 8 is very clear, right? That there was a pre-existing crack and then this is going to grow. Second, the example I'm going to give you with respect to steel. Okay. So let us have a crack here. So it's a pre-existing crack. So first point says that this crack can itself grow and it can lead to the cleavage fracture. Second, you can have a crack, main crack, and then you are going to generate another crack in front of it. So something like this. Now, because of the stress concentration, of the previous crack or pre-existing crack, you have sufficient amount of stress or the new sufficient amount of stress for the newly formed crack to grow. Okay, so because of the stress concentration of the previous crack, you have sufficient amount of stress for the newly developed crack to grow. Okay, and that will lead to the cleavage fracture. So this means that there has to be discontinuity, right? There has to be some discontinuity ahead of the main crack. So a sharp microcrack ahead of the main crack can be treated as Griffith crack okay, and propagate into the matrix which can lead to cleavage fracture. Okay, and remember, note the main crack provides sufficient stress for microcrack to grow. Okay, so in this case, you have this as main crack or pre-existing crack, and then you are developing some micro crack ahead of the main crack. Now, because of the presence of main crack, you are having stress concentration, and that is sufficient for this micro crack to grow. Okay, that means there should be some discontinuity in front of the main crack so that you can develop micro crack, right? And what is that discontinuity? This can be second phase particles. Okay, so in ferritic steels, you can see this phenomena happening that you have a main crack, and then in front of that, suppose you have a particle. Okay, so you can develop a micro crack because of the cracking of this particle. And this is particle. Main crack or pre-existing crack. Okay, so example in ferritic steels, second phase particles such as carbides or inclusions. Okay, they can create sharp micro cracks. Okay, because of the incompatibility, because the second phase particle is going to have different property than the matrix. So there is an incompatibility between the particle and the matrix, which will lead to the generation of crack. We saw the similar phenomena while we were talking about ductile mechanism, right? Ductile failure mechanism. Due to incompatibility with matrix. Okay, so overall, if you have a pre-existing crack, which is main crack, it can itself grow if it has a sufficient stress concentration. for it to grow, or it can generate a microcrack in front of it, ahead of it, right? Which can then grow, leading to the cleavage fracture. And one of the example is that you have discontinuity in terms of inclusions of second phase particle which are going to crack, which will lead to the formation of microcrack. Okay, so this is what is happening when you have pre-existing crack. Now, what happens when you don't have any crack, right? So there has to be some local plasticity, and then dislocations come into picture. Okay, so although overall it is a brittle failure, locally you can have plastic deformation at a very local level, which will lead to the movement of dislocations, and then those will lead to the nucleation of cleavage tract, and then it will eventually grow. Okay, so the second condition is if there is no pre-existing flaw, okay, or even if there is a flaw, it is not able to grow. Okay, so in this case, local yielding is necessary. Okay, for slip, and this will lead to the generation of cleavage tract. Okay, so or nucleation of cleavage tract. So now since we are talking about movement of dislocation and slip, etc., remember overall material is brittle. We are talking about locally what is happening now. Plastic deformation is locally, right? So here now mode 2 becomes important also. So there are several dislocation theories. I'm going to quickly discuss some of them. Okay. So again, remember local yielding, huh? And then there are dislocation theories. The first one is proposed by Jenner and Stroh. So they propose that the dislocations are moving again locally in a slip plane. Okay, and then they are going to pile up at the drain boundaries. Okay, similar to the pile up we discussed when we are talking about drain boundary strengthening mechanism. Okay, so pile up of dislocations against drain boundary. Now you are going to nucleate tract when you have sufficient number of dislocations in the pileup. So tract nucleation when sufficient number of dislocations. Okay, at the tip of or at the tip of pile up are squeezed. I will show you the schematic for better understanding. And whenever this happens, this will lead to wedge track or cavity. Okay. So you have a boundary, dislocations are getting piled up against that drain boundary. And if you have sufficient number of dislocations at the tip of the pileup, they are going to get squeezed, leading to a wedge track. I will show you the schematic now. So suppose you have a pileup, okay, and then you have dislocations. Okay, something like this, and your drain boundary is somewhere here. Okay. So you have now sufficient number of dislocations here. Okay. They are getting squeezed in these locations, right? Okay. So now you are generating a track. So this is like a track. Okay. Call it wedge track. So you have slip plane here. Okay. So what is happening? You have a slip plane. Dislocations are moving on this slip plane and they are getting squeezed. And remember, this is like half plane, right? So you are going to generate a sort of void in this region, which is like a wedge track. Okay. And this is how you generate cleavage track. Now, since you have generated cleavage track, I will talk about the growth eventually, and then it will lead to the fracture, cleavage fracture. Okay, so this is one of the mechanisms. Another one, see here also, if you remember, when we are talking about drain boundary strengthening, I also distribute Cottrell formula, right? So at a distance R, you know what is the stress value because of the pileup. Okay. So in this case also at a distance R, if the stress concentration is sufficiently high, you can generate track in front of the pileup. Okay. Because you have sufficiently high stress because of the pileup at the drain boundary. Okay. Now second one is Cottrell mechanism. So this was discussed in terms of Lower-Cottrell barrier in the lecture 1 or course 1. So Cottrell proposed that there are two slip planes, dislocations are moving in that on that slip planes, and then they are going to interact the dislocations, and if they fall in the cleavage plane or not a slip plane, they are not going to grow. Okay, and then there will be pile up of dislocations on both the slip plane. Now, if that happens, that is called Lower-Cottrell barrier or Cottrell barrier, and it will lead to the formation of crack. Okay. So if you remember, you had these slip planes, slip plane 1, slip plane 2, and then you have another plane, say this is 001 plane, which is cleavage plane. So it is not a slip plane in FCC crystal. So you are going to have dislocations. Okay, now these dislocations are moving in this slip plane as well as this slip plane, but now they are interacting here. Now they cannot move, so you are going to generate a track. Okay, because again, you can think of in this squeezing phenomena, or because of the pileup, you have very high amount of stress, which can lead to the generation of crack. Okay, so this is like Lower-Cottrell barrier, another one, another mechanism. Then the last one is the similar to what we discussed in terms of the inclusions. Okay, so you have the presence of second phase particles. Dislocations are getting piled up locally against that second phase particles, and that second phase particle is now going to fracture because of the sufficiently high stress at the pileup, okay, which will lead to generation of cleavage crack. And this is typically observed, say, in steels. In steels, it was observed that brittle carbides play an important role in crack nucleation. Okay, so suppose you have two grains, and then at the grain boundary you have carbide. So this is your carbide. Okay, now inside the grains you are going to have pile up of dislocations. So say something like this. Locally. Okay. Now, because of this pile up, you are going to have sufficiently high amount of stress that will lead to the fracture of this carbide particle. And you are going to form microcrack in the carbide. Now, once you have formed, this can now grow. Okay. So, pile up of dislocations leading to sufficient stress at the pile up. Okay. Now this can nucleate crack in grain boundary carbide. Okay, so overall, I have discussed about two types of mechanism. First one, where you already have a presence of crack. Now this crack has sufficient stress at the crack tip and it is growing, leading to the cleavage fracture. Second, the crack is there, but it cannot grow. But what it is doing, it is generating a micro crack in front of this, okay, and then they are combining, leading to the cleavage fracture. That micro crack can nucleate in some discontinuity. For example, you have inclusions or second phase particles. That is the mechanism one when you have pre-existing crack. Now there could be a situation where you don't have pre-existing crack, or even if it is there, it is not going to grow, right? And there is a very nearby, there is no local discontinuity, right? So what could happen? You have to have locally plasticity, right? Locally plastic deformation, which will lead to the movement of dislocations. So several dislocations theory have been proposed. Okay, I have discussed here. So this is say number one, number two, and number three. So we have generated new track, this cleavage track. Now this cleavage track has to grow and finally lead to the fracture. Okay, So when they grow, they are going to generate different patterns. Like in ductile fracture mechanisms, we talked about mostly dimples, right? And tunneling also. That is also that is like macro. That dimples is micro, right? Similarly, when we talk about cleavage fracture mechanism or brittle fracture mechanism, we have different patterns if you look at the fracture surfaces. Okay, so what are those? So you can have macro as well as micro. Okay. So macroscopic features, and you can also have microscopic features. So in microscopic, you can have chevron or herringbone patterns, or you can have radial marks. In microscopic, you can have river pattern, very important. Like, dimples, in most of the cases, when you talk about cleavage fracture, you are going to see rivers marks. Okay. So river or fan pattern. In some books, you will see fan pattern. And second, you can get tongue. Okay. So we'll discuss one by one these, but we'll mostly focus on the formation of river pattern, which is one of the most important features you are going to observe when we talk about cleavage fracture. Okay. So let's talk about now river patterns. Okay. But before that, since now we are talking about the growth, let me tell some of the facts for when we talk about cleavage tract growth. Okay, let me now delete it. So when we talk about cleavage tract growth, it's a rapid propagation of tract along a particular plane or orientation. Okay, so it's a rapid propagation of tract, not like ductile mechanism. Okay, and it happens along a particular orientation or particular plane, and that's why we call it cleaving. Right? Now, what are those preferred planes? So preferred cleavage planes are first lowest at packing density, so you have lowest packing density in that particular plane. That means you have to break very less bonds, and that's why it becomes a preferred cleavage plane. So fewer bonds will be required. Okay, to break. Second, if it is a lowest packing density, second is spacing between planes is higher. Okay. So example is, if you talk about BCC metals, you're going to see cleavage along 100 planes. Okay, so it has lowest packing density and the spacing between plane is higher. That means when you break a bond, since spacing is higher between two planes, when you break a bond, you require lower amount of stress, right? Because the distance between two planes is higher. Okay, so in general, FCC is not very much susceptible to cleavage fracture. Okay, why? Because you have lots of active slip systems. BCC and SCP metals and alloys can show cleavage fracture. In fact, the metals and alloys which are not showing cleavage fracture in one condition can show cleavage fracture in another condition. Okay, severe condition. And what are those conditions? So that the material can become brittle, which were ductile before. So there are a few conditions. The first is low temperature. Second is high strain rate. Third is presence of notch, crack. Fourth is say corrosion. Okay. So although some of the metals and alloys, they are ductile, if we have these four conditions, combination of these four conditions, the material can show brittle behavior. Okay. Low temperature, high strain rate, presence of notch and crack, and corrosion. So corrosion is also very important, right? In the absence of corrosion, you might see it is having ductility, it is showing ductile behavior, but in the presence of corrosive medium, it might show brittle fracture. Okay, so these are the four conditions. So now let's go back to the beaver marks. We are now talking about the growth of the cleavage tract which has been nucleated. Okay, so these are your microscopic features. So you are going to have, when we talk about cleavage fracture, remember that if you talk about cleavage, so cleavage tracks show a straight path with global fracture surfaces appearing in plane and smooth patterns with little evidence of plastic strain. Okay, so it says that cleavage tracks are showing the straight path and the fracture surfaces, if you see global in the macroscopic. So this is like macroscopic we are talking about. Okay, so macroscopically, if you see, it will show you a very smooth plane, okay, or pattern, and those are called cleavage plane. Okay, I will show you in the next lecture or probably later all these microstructures, okay, or micrographs of the fracture surfaces. Okay, so now river marking. So you have multifaceted surface in polycrystalline material. Here each pattern or each facet corresponds to a single grain. And what you are going to see is river marks or patterns on each facet. Okay, which is like multiple lines or ridges converging to a single line. Okay, so macroscopically, if you see the fracture surface, you are going to see facet, right? A very smooth plane. So if I have a polycrystalline material, so suppose you have grains, and after it has fractured, so suppose it fractured like this, suppose, right? So this is your crack. So you are going to see these surfaces as facets. So say this particular grain, so this is like facet. So if you just break this into two parts, you are going to see very smooth surface that is facet. And that is what I have mentioned here, that you are going to have multifaceted surface in polycrystalline material. Since this is a polycrystalline material, it is going to contain lots of grains, right? So you are going to have multifacets in the fracture surface, and each facet will correspond to a single grain. So in this case, say this is number 1 facet, this grain will show number 2, then number 3 and number 4 and so on, depending upon the number of grains you have. So this is a number 3 and here you have say number 4. Okay, so each facet will correspond to one grain. Now if you see that particular facet, you are going to see lots of marks, and those marks are called river marks. So it's like you have a line and then you see multiple lines going like this. So it's like a river. Okay, and that's why this is called river mark. And you are going to see this in one facet. Okay, so each facet you are going to see river marks. So this is like a facet. So how and why does this river marks form? So let's talk about that formation of river marks. Okay, so suppose you have a crack, cleavage crack, it is growing in one grain. Okay, that will lead to one facet we have discussed. And now it is now interacting with a grain boundary. Okay, so a propagating crack reaches the grain boundary. So what is going to happen as soon as it reaches, initially it had some cleavage plane. Now the cleavage plane is going to change because each grain has its own orientation, right? Suppose you have a crack. So this crack was growing in this direction. As soon as it interacts, it reaches to a grain boundary, you have another grain which has a different orientation. So cleavage plane is also going to be different. So now this particular crack has to change its path, okay, to another cleavage plane in another grain. Okay. You are going to have nearest cleavage plane in the adjoining grain is oriented at a finite twist angle with the current cleavage plane. Okay, so now let me mark this as a grain 1. Now you are going to have another grain 2. Okay, so the current cleavage plane is this guy. So this is, say, my current cleavage plane in grain 1. Okay, so as soon as this cleavage track reaches to a grain boundary, something like this, now the grain which is on the other side, on this side, it has different orientation, right? So cleavage plane is not going to be at the same line. So cleavage plane is not going to be like this again, right? It is going to be at certain angle, and that is what I have written here. Okay, so the nearest cleavage plane in the adjoining grain is oriented at a certain twist angle with the current cleavage plane. So initially, track accommodates this twist mismatch by forming tracks on several planes. Okay, and as these tracks on the several planes they grow, they join by tearing between the planes. So as multiple tracks propagates, they join by tearing between planes, or say parallel planes in this case. Okay, so tearing will happen of the ligament. Okay, so ligament, say ligament between planes. Okay, so what is happening? You have a crack which is coming there. It is going to interact with the grain boundary. It is going to reach to the grain boundary. Now it sees another grain where the cleavage planes are at a certain angle. So to accommodate this twist mismatch between the two grains, you are going to form multiple cracks on the parallel planes. All these are cleavage planes on the another grain. Now they are going to grow, and as they grow, there will be some ligament left or material left between these two parallel cracks. They are going to join. They are going to tear. Okay, and then the cleavage track propagates. Now, after, since you have formed lots of this track, they are going to consume lots of energy, right? To minimize that, after it has grown to certain length, they form or they join together and become a single crack. So, since propagation of multiple cracks require more energy. All cracks try to merge. Okay, and this leads to single crack. Okay, now let me draw the schematic so that you can understand better. So overall, now you know, right? You have a track, cleavage track. It reaches to the drain boundary. Then on the parallel planes, cleavage planes on the another drain, which is number 2 here, you form multiple cracks. And then they grow by tearing the ligament between those cracks. And finally, they merge together. And that's how you generate river marks. So you have, say, multiple cracks. And then they merge finally to form a single track. Okay, and these cracks are parallel cleavage planes. Okay, now you can see here, right? It's like a river branching, and that is why it is called river mark. And again, this is happening in a single drain, right? So say this was your drain 2, and here you have drain 1. Okay, so let's see you have a original cleavage plane like this, a current cleavage plane. Okay, and then you got another one which is at a certain angle. It's something like this. Okay, so you have two planes. I hope you can imagine in 3D. And then you are having multiple cracks. So you get one crack, okay, and then okay. So this is your second cleavage plane or in the second grain, right? So next cleavage parallel planes, and this purple one is the original one. It's a current grain, right? So this is your current cleavage plane. And the angle here, you can see this angle here. This is your twist angle. Okay, so you have two planes and they are at an angle. So twist angle. Okay, and all these are your cleavage plane, parallel cleavage planes. This is not, sorry, parallel. So this is your cleavage plane. So these are cleavage plane which is parallel. Okay. And finally they are going to merge. So this is what is happening after merging. So this is like a single crack here after they merge together. Okay. So overall, if you see river patterns, can indicate the direction of track propagation in a drain. Okay, so you now know that if you see river patterns in a drain, there will be multiple planes, and the ligament between them will, they will tear, and finally you are going to see a single drain like this, a single plane like this, single track like this. Okay, so now if this is happening, the track propagation direction is this. Okay, so by looking at the feature, you should be now able to tell what is the track propagation direction in that particular drain. It might change between the drains, right? Overall, the track growth could be something, but locally it might change here and there. So this is about the river pattern. So now let me talk quickly about the tongue as well as chevron and the radial patterns very quickly. So tongue. Again, this forms during propagation. Okay. So it forms when cleavage tract meets a site of deformation twinning. The cleavage tract continues to form on the interface of the twin boundary, eventually sticking out like a tongue. Okay, so here twinning becomes very important, and these turns they form when cleavage tract meets a site of deformation twinning, and then this cleavage tract continues to form on the interface of the twin boundary. Okay, so there is a twin boundary, and at the interface it forms, and eventually it just comes out like a tongue. Okay, so that feature is called tongue. So if you have a surface, so if you see the schematic, it will look something like this. So it's like sticking out. This is tongue. Okay, this is also microscopic feature. Okay, now let's talk about the remaining two in microscopic, which is chevron and radial mark. Okay. So chevron or herringbone, and second is radial. So if you see chevron and herringbone, they will form at an angle. So chevron, so these patterns will be at an angle. Herringbone it will be at a particular angle of 90 degree. Okay, so both will be forming an angle. Chevron is in general, herringbone is at a particular case when theta is 90 degree. Okay, so both are V-shaped. Angle is different. Okay, and you are going to frequently observe this in low strength steel. Okay, so what is happening here? So Chevron pot pattern points to the origin of fracture, basically initiation. Okay, and how it is forming? So Chevron patterns are caused by discontinuous region of cleavage type brittle fracture joined by regions of shear that the Chevron features are regions between cleavage and shear zones. Okay, so first when you see Chevron pattern, so let me just draw the schematic. So you have initiation and then you are going to see Chevron patterns like this on the fracture surface. I will show you that. Okay. So this is like crack initiation here. And then these are your Chevron patterns. And remember, this is happening during growth. Okay. So when you see the V-shaped mark, you should know that this is Chevron pattern. And also remember, you will see this is a macroscopic feature, right? So these are large features. Okay. So if this is a V mark, you know that the track has initiated somewhere here. Okay. At the bottom of the V. So that is the crack initiation point, and that is what I discussed here in point number 1. So Chevron pattern points to the origin of fracture initiation, right? So we know. Now the second is Chevron patterns are caused by the discontinuous region of cleavage type brittle fracture. So here you are going to have cleavage type brittle fracture as well as there are regions of shears. And between that, those two, you are going to have ligament, and whenever it fractures, you are going to form Chevron patterns. Okay, so this is what I wanted to talk about Chevron pattern. Now let's finish this lecture by discussing about radial marks. So radial marks, if you see, you are going to have crack initiation site. And then you are going to see features like this. Okay, so these are your radial marks. Similar to the chevron mark, if you see radial mark, it's like growing outward, where the crack has initiated. In this case, it is in this position. And the marks are growing out radially. Okay, so radial marks typically fan out from the initiation site. Okay, so overall, for the fracture mechanisms, we started talking about the ductile fracture mechanisms. I introduced the concept of dimples, etc. Okay, cup and cone fracture, rupture, those are ductile fracture mechanisms part. Today, I discussed about the brittle fracture mechanisms or cleavage fracture, right? And its nucleation in terms of either the pre-existing crack or local plasticity, right? And then the growth in terms of patterns such as radial pattern, then chevron, river marks, tongue, etc. Okay, so we have completed the topic of fracture mechanisms. In the next lecture, we will discuss about fatigue crack growth, okay, or fatigue testing. Okay, and finally, we will conclude this whole course by talking about creep testing. Okay, thank you.